Hello and welcome to this complimentary webinar looking into the capabilities of the geometric suite of data analytics solutions. The presentation today will deal with the MODDE Pro 12 software, and it has the title Looking Beyond the Fractional Factorials for Screening DOE. Those of you that have attended earlier webinars in this series in looking into the capabilities of the geometric suite of data analytics tools will recognize that there is now a little different touch to the graphical outline of the presentation. And that is because that the geometric suite of data analytics is now part of Sartorius Sterim Biotech since about a few days ago. And that is why the presentation look a little different. Here we see on this slide where we are right now in the webinar series. We are going to look in at some more advanced options that are available for screening DOE. In this presentation, we will be assuming some prior information and experience with the MODDE Pro 12 software. If you are looking or lacking the basics into the MODDE Pro 12 software, I would like to refer to an earlier webinar that was broadcast a couple of weeks ago where we're going through the basics of the MODDE Pro 11 software. So this is where we are today, and in a couple of days, Tuesday next week, we will make a follow-up presentation to the presentation today, but looking into options for RSM DOE, more advanced stuff. Here we see a little introduction of today's presentation, and we will concentrate today on screening designs that work with when the experimental domain is regular. So in a general sense, you can say that screening is always used to identify a few significant factors from a rather large number of potentially important ones. And the most frequently put forward recommendation using the MODDE Pro 12 software are designs drawn from the fractional factorial design family. But as I told you, they apply when the experimental domain is regular. If you would like to know the capabilities of fractional factorial designs, we refer to other recordings in this series of complementary webinars. The presentation today outlines additional design families which can be used for screening regular experimental domains. And the designs that we're going to concentrate on today are part of the Plackett-Burman design family, the Rechtschaffner design family, the L designs, and also the new addition of definitive screening designs. Before we go into some of the properties and hallmarks of these designs, first just a little note on what we mean with a regular experimental domain versus an irregular experimental domain. So a regular experimental domain that is in focus in this presentation means that you can map it using classical DOEs, classical fractional factorial designs, classical central composite designs, and so on and so forth, and that the experimental region is not mutilated by some sort of constraint, chopping off a corner or making some part of the experimental domain inaccessible for experimentation. This thinking of regular versus irregular experimental domains also apply to the situation of mixture design, where you sometimes have regular regions looking like triangles, simplexes, or hypersimplexes. Sometimes you're working with more irregular experimental domains. Regardless of whether you're working with screening, optimization, or mixture design, if you run into a situation where the experimental region is irregular, you're going to have to address that with the optimal design. And we have other presentations on the optimal design and will not dwell on that anymore today. Whenever you are inside the MODDE wizard and you have defined all the factors that you can vary, the design wizard will list a table with all the designs that are eligible in a given application or given situation. And this list will also have recommendations. There will always be a first recommendation and a second recommendation, and both these designs would then be very good to address the problem at hand. Sometimes the list can be rather long, and then you will have to start to select the design based on consideration of how many experimental runs is required or encoded by the design family in question, and whether it, in this case, because it is a screening thing, support a linear or an interaction model, or maybe even a partial quadratic model. Whichever experimental protocol you highlight in this list will also be having a little description in the lower part of this window or of this page. So we will today be discussing definitive screening design, Rechtschaffner design, different versions of the L family, and the Plackett-Burman design. These are the things that we will discuss today for the screening situation. Fractional factorial designs, they are popular because they encode less experiments than full factorials, and they are called fractional because you are making a fraction of all possible corners, and often you're selecting a half fraction or maybe a quarter fraction. And in the little illustration here, using the famous cake mix example drawn from our course documentation, you can see how you can divide the full factorial design in 3 factors into 2 equivalent half fractions denoted 2 raised to the power of 3 minus 1 fractional factorials. The advantage with fractional factorials is reduction of experiments. The drawback or the negative aspect is that you get confounding of effects, and we are not going to discuss that anymore today. Now, the alternatives to fractional factorial designs will now come on the coming slides, and we will start with the Plackett-Burman designs that were introduced in 1946. These are also, like the fractional factorials we were just briefly reviewing on the foregoing slide, 2-level designs, meaning that you have to define at least a low setting and a high setting for each investigated factor. They have the resolution 3, which means that you have a very complicated confounding pattern, and that's why these designs only support linear models. If you go back to the design wizard page, you will see that as soon as you select a Plackett-Burman design, the supported model is a linear of the linear type. These are very compact designs. They require very few experiments per factor, and the interesting feature is that the number of runs is a multiple of 4, and that means because fractional factorials can give you 8 and 16 and 32 runs, it means that Plackett-Burman designs neatly cover the gap that exists between 8, 16 and 32. For instance, in terms of the 12 run, 20 run and 24 run counterparts, they are of particular interest. In some situations, you should also be aware that the Plackett-Burman design can actually be a specific fraction of a factorial design. But if you have a choice between a Plackett-Burman design and a classical fractional factorial design with the same number of runs, we recommend you choose the fractional factorial because it will be easier to upgrade that design by adding more experiments should that be needed. So as I told you, the Plackett-Burman designs are very complex designs. It means that you can actually investigate the number of factors you can investigate will be 1 less than the number of runs. So for instance, if you would go for the 12-run counterpart or member of the Plackett-Burman design family, you could in theory investigate up to 11 factors, but maybe 9 would be a more recommended choice because you would then have some degrees of freedom left over for residual analysis. In the screenshot here from the MODDE software, where we are looking at what we call the correlation matrix, we are looking at the correlation matrix for 11 factors being mapped in a 12-run experimental plan, and you can see that we have a high degree of confounding. Another alternative to the fractional factorials is the so-called Rechtschaffner design family that were introduced in 1967. These are also orthogonal designs. They are of resolution 5. They are fractions of the 2 raised to the power of n and 3 raised to the power of n factorial designs. And that means that they can be used both in screening DOE, then we're working with the 2n fractions, but also in RSM or optimization, then we're looking into the 3n fractions. And this optimization alternative is something we will come back to in the presentation in a couple of days from now. The interesting thing is that in screening is that Rechtschaffner designs allow us to estimate all the main effects and all two-factor interactions without confounding, or only with partial confounding at least. The number of runs is seen here by this expression, and in the screening context you can say that the Rechtschaffner designs represent what is called saturated two-level fractional factorials of resolution 5, and they are then used with interaction models. Saturation in this case means that the number of terms in the model will be exactly the same as the number of factorial points in the design. So you will have no degrees of freedom left. So for 3 factors it means the Rechtschaffner screening design will have 7 runs, 4 factors will have 11 runs, and so on and so forth. And in this number of runs it does not include any replicated points. Resolution 5 means that the two-factor interactions are not confounded with other two-factor interactions. We will be using an application dealing with DOE and nuclear waste cementation later on in the MODDE software, where 4 factors in 2 levels are studied. If you would have opted for a full factorial design in this application, it would have meant around 19 runs. A fractional factorial design would have encoded around 11 runs, and the Rechtschaffner design used in this application contained 14 runs, 11 corners because 5 corners were dropped, leading forward to the saturation condition. And the application that we will be illustrating in the MODDE Pro 12 software towards the end is taken from this original literature source. The third type of design family that we will cover in this presentation are the L designs. This is a group of so-called orthogonal arrays, and they were at least heavily promoted by Genichi Taguchi in the 60s and 70s. These designs are 3-level or mixed-level fractional factorial designs. When we say mixed level here, it means that you can have some factors at 2 levels and some factors at 3 levels. That is what we mean with the notation of mixed level. MODDE has 4 L designs implemented, all of which initially support linear models, but I will challenge this a little later on. These 4 L designs are the so-called L9, L18, L27, and L36, where the number close to the uppercase L simply means the number of runs in the worksheet, excluding any replicates. So you can see that the ones that are implemented in MODDE has the number of runs in steps of 9 runs in between, and they work at maximum up to 13 factors. The one that is mixed is L18 because it has 1 factor at 2 levels, and some of the applications that we have seen relating to or using L18 often then has a qualitative factor as the 2-level one, something that is on or off or present absent, for instance, or solvent A and B and so on and so forth. Some of the properties of the L designs, well, as I told you, when you select a design drawn from this family, MODDE initially lets you select only the linear model because the 2-factor interactions are not estimable. But in contrast to the Plackett-Burman designs, where you have linear models only, and the Rechtschaffner designs where you have interaction models, the L design actually allow you to selectively estimate, to selectively include square terms in the model to be estimated, and that you can do in the edit model dialog. So this thing of being able to introduce selectively quadratic terms, that is of course on conditional that the factor you are opting for a quadratic term for has been examined at 3 levels. So that means that if you are anticipating a quadratic behavior, you may choose an orthogonal array such as an L design. The last family that we are discussing in this presentation is the definitive screening design. This is a fresh addition into the MODDE Pro 11 software that was released about 1.5 months ago, and I was earlier pointing to the release webinar. This is a new implementation. The originators, I should say, behind this design family are Jones and Nachtsheim, hard for me to say, sorry for that, in 2011. The interesting thing to know is that these designs are only available when there are at least 4 factors in an investigation. These designs are truly parsimonious. It means they are very condensed, very compact, requiring extremely few runs. So if the number of runs, the number of experiments is an issue because of cost or time or whatever, and if you're also perhaps anticipating quadratic behavior, these designs are definitely of relevance to at least look into. All factors are here tested at 3 levels. And the default regression model is a model with linear and quadratic terms, but no 2-factor interactions, because they will be heavily confounded. And one should also know that the quadratic terms are partially correlated with these designs, and these correlations get worse and worse the more number of factors you have in the DOE. We will look into a series of correlation matrices where we will look at how different terms of the models are correlated or uncorrelated. Here on this slide we see a little overview as far as the number of runs is concerned, and I will come back to this slide. It is duplicated and is coming back towards the end of the presentation. But we have here a little overview running from 2 factors up to 10 factors. For comparative purposes, we have the number of runs required by the fractional or the factorial or fractional factorial designs, the Plackett-Burman designs, Rechtschaffner, L design, and the definitive screening design. And if it sets int, it means the supported model can support 2-factor interactions. If it says lin, it is a linear model, and if it sets quad, it's a quadratic model that is supported. So we will come back to this table towards the end, and I have a few comments on the number of runs and some recommendations. We start now with some comparisons, and we have selected to make a comparison for the situation when the DOE protocol contains 6 factors. If you would select the fractional factorial design, for instance, it would support a linear model. And if you go into the correlation tool in the MODDE software, you would see that the linear model with 6 terms, then because we have 6 factors, would contain terms that are fully orthogonal, fully uncorrelated, which is the desirable situation. The ideal situation is that you have 1 on the diagonal band, because when you correlate one term with itself, it is of course obviously fully correlated with itself, and 0 on the off-diagonal elements, meaning that in this case you can estimate the coefficient of x1 completely free of any disturbance or contribution from the regression coefficient of x2. Whenever you have values here that are not 0, the net result is that the confidence intervals displayed on the coefficients in the coefficient plot will get larger than otherwise. So any non-zero value here will cause inflation, increase in the confidence intervals on the coefficients. Another alternative requiring more experiments is another fractional factorial design, in this case supporting an interaction model, and again all the terms are uncorrelated. If you go for the Rechtschaffner design, where you start to drop corners until you are down to the number of corners in the design equaling the number of terms in the current regression model, you will see that you get correlations among the terms in the correlation matrix. But these are still, in this case, quite small. They are around 0.1 or minus 0.1 in all cases, which is relatively uncomplicated. If you take the L27 and expand the model from a linear one to a quadratic one, you will see that all main effects or all linear terms are completely free of one another, and there is no mixing up between a linear term and the quadratic term. But for the quadratic terms, you start to get some correlations, as is indicated here. I should also point out that the threshold here of 0.3 that refers to when a cell in the correlation matrix will become colored. It's just a little diagnostic help. Here we have the definitive screening design with the quadratic model. This is a design with comparatively few runs across these 6-factor comparisons. It is one of the designs with the smallest number of runs, but the price you pay is that the quadratic terms become significantly correlated in this case. So this brings us over to the demo of the MODDE software, and I will do the demonstration in 2 steps. First, we will look into, let's say, the experimental mode or sandbox mode of MODDE. I mean, we are going to use some shortcuts to quickly define factors, just to get an overview of what a certain design in a given situation will require from us as far as the number of experiments is concerned. And this experimental mode I'm talking about means that you can very quickly configure factors. I'm just calling them x1 and x2 and clicking on the return button on the keyboard to quickly define a couple of factors, because I want to make a little range finding study, and I'm not really concerned with whether the setting is the correct one. I just want very quickly to get up to the correct number of factors. I can then click next, and we can also define a hypothetical response. It will not influence. Then we are at the stage or in the page in the design wizard where we select the objective, and today we are focusing on the screening entry, and in a couple of days we will do the same thing with the optimization or RSM entry. Then here you see on the next page where you select a model and the design. And as I told you, you have the fractional factorials with different resolutions. You have a possibility also to choose a definitive screening design. You can also choose the Rechtschaffner. In this case, there are only 3 L designs possible. The L9 has too few runs to work when you have 6 factors. And you also have the Plackett-Burman. You even have a Plackett-Burman supersaturated, but supersaturated designs in DOE we cover in a separate presentation. So you can then select any design that you prefer. You see the number of runs here, the type of the model, and then if there is a possibility to link to the resolution, going back to the complexity of the confounding pattern. We are also indicating in the name the resolution and the pseudo resolution if that is of relevance. We can then select any design, for instance the Rechtschaffner, say finish, and then the worksheet is created. One of the tools that we often use to investigate in this sort of range finding study, to investigate or understand the performance of the design, is the so-called condition number. And I'm now pointing in the lower part of the of the screen where you can see it is called cond nu, and it is 1.59 in this case. The condition is an performance measure, and it indicates the sphericity of the design, you can say. And for a screening DOE, you normally find the condition number in the range between 1 to 2 or maybe up to 3. The lower and optimal number for the condition number is 1.0. It can never be smaller than 1, and if it is 1.0, it means you have a perfect orthogonal design. And when you look at the correlation matrix, the correlation matrix will have only ones on the diagonal and 0 everywhere else. In this case, we have a condition number of 1.59, and that means we will have partial correlations as seen in this correlation matrix. We will have partial correlations among the terms included in the model. If we are not happy with the property of this design, well, then we just go back to the design wizard and select something else. We can select a definitive screening design and say finish, and then MODDE is just telling us that now you're giving me new input. I would like to forget about the previously generated design and create a new one, and that's basically what you're doing. Now you can see the condition number here, it is higher. You can also look at the correlation matrix. If you have a higher condition number, it means more a larger extent of correlated terms in the model, and you can then visualize the correlation, for instance, through the correlation matrix. We will now go back to the real application that I told you. It deals with the application of DOE in nuclear waste cementation, and if you read some of the background information in the original literature source, it is mentioned that cementation in this case is a routine procedure that is used to encapsulate radioactive waste generated at nuclear power plants. And one of the challenges that can arise is that sometimes some components or ingredients of the waste, there is a risk it may react chemically with the cement phases or even the mixing water. And these reactions are partly undesirable because they are difficult to control. They can accelerate the cementation process, but they can also retard it, slow it down, or maybe even inhibit it. And some of the consequences of these reactions is that the cementation part the cement can start to swell, and that can lead to cracking of the cement material, and then there is this security issue. So in this investigation, they are looking into 4 factors and its influence on this swelling. So the type of factors that are studied is 2 types of cements. This is a qualitative factor, and it has the setting cement of type 3 and type 1. It is the oxide density, which is a qualitative factor. The oxide density indicates obviously the density of the oxide in the nuclear waste. The third factor is what is called the incorporation rate in percent, and it indicates how much waste is incorporated in percent of the cement weight. And the last factor is a ratio between water and cement, because this ratio will influence the plasticity and the workability of the grout. And the response is then indicative of swelling. It's called length variation after 90 days. It is measured after 90 days in room temperature, and it is measured in micrometer swelling per meter, and this is something that should then be minimized. The closer to 0, the better, indicating no crack formation or deleterious modifications to the cement. This is a Rechtschaffner design with 11 experiments, and there are 3 replicated points. It is the combination of experiment number 5 that is replicated 3 times in the lower part of the worksheet. And we can see here that there is a variation between around 250 up to 5,000 micrometer per meter, or somewhere between 5 millimeters down to a tenth of a millimeter over these 90 days. We can see that the condition number is 3.44, and that indicates some significant correlations among some terms in this default interaction model. And We can see from the red band here in the correlation matrix that the highest correlations are found among the two-factor interactions. We will now use the MODDE analysis wizard to analyze the data, and remember the objective is to minimize this length variation. The first step in the analysis wizard is a replicate plot. You can say that the analysis wizard corresponds to a guided workflow throughout the most essential steps in the data analytical stages of DOE. It's a guided workflow ensuring that you are going through all the critical steps in the correct order. Now it says that the summary of fit plot cannot be calculated because it requires more degrees of freedom. We have a saturated situation. We have as many terms in the regression model as we have runs or corner points in the factorial design or in the Rechtschaffner design, excluding the center points. The replicate plot shows that we have small variation in the replicates compared to variation across all the points, and as the advisors say here is that the variability of the replicates is small, and this will likely result in a very useful model. The next step is the histogram plot, and I will now show you what it looks like initially. Initially there is no transformation applied to the response. So when you have done the replicate plot and come to the histogram, then what is called the skewness test has been triggered. We have this yellow triangle here indicating that there is an issue with this plot according to the auto-tune, auto-fit model capability of this analysis wizard that is called the one-click option. We can do a one-click thing, more of a black box analysis, but I'm stepping through all the steps to show it. So we will then auto-transform, and then we see what happens with the distribution of the response after taking, in this case, the logarithmic transformation. Results are improved. We then see the model, and now we have a lot of terms in the model. It may look like a numerical jungle, whereas it is not. In reality, all these terms arises because we have some of the factors being qualitative, and whenever you're forming a cross term involving a qualitative factor and some other factor, you will have this split. We can start to fine-tune the model by dropping some terms that are small, and after a while we will have reached a situation where we have a very good model. We see that there are among the linear terms two things that affect the swelling or the length variation, and it seems that if you're using cement type 1 because the coefficient is going down, that is beneficial. Cement type 3 would cause much higher length variations, much more swelling, you can say. So definitely, judging from the coefficients, the cement of type 1 is the preferred one. The other thing that has a huge influence is the incorporation rate. And the higher the incorporation rate, the quicker you're incorporating the waste, the faster or the larger is the swelling. So a low incorporation rate corresponds to a lower risk for swelling. And then there is some influence from the oxide density indicating that if you're running on or using oxide of a high density, you have a lower risk of swelling with cementation. We can also follow up on this through other types of plots. But first, let's just complete the analysis wizard. We see the summary of fit plot and what these bars mean and how to interpret them. We refer to other recorded webinars. The residuals, the normal probability plot of residuals is very good, and it suggests no deviating experiments. And here we have the final plot, which is the famous observed versus predicted plot of the swelling or the length variation. Finally, when exiting the wizard, there is a little summary page, and if you would have had more responses, those would have also been summarized, or the models would have been summarized just as one row per response in this final summary page. There are different plots you can use in the MODDE software to visualize the result. One of them is a 4D contour plot, 4D because you have, you can say, 4 factors. And here we see how the swelling or the length variation is predicted to change when you're changing 4 factors. And these response contour plots are consistently color-coded across all the plots. So it means that where you have the largest dark blue area, that is where you have the most beneficial condition for a very low length variation. And it turns out to be in the lower right-hand part that you have the largest blue area. So a low incorporation rate using a low water cement ratio, using the cement type 1 and having a high oxide density. These are the conditions corresponding to a situation where you have very stable cement with little or no change in the length, or indicating stable product, stable encapsulation, and little risk for crack formation, and so on and so forth. This was the last thing I wanted to demonstrate in the MODDE software. Let's go back to the PowerPoint part for a few final remarks. So what we have said in this presentation is that there are alternatives to fractional factorial designs for screening DOE. Plackett-Burman protocols are often popular because they are very compact, and what we really like with those is that we have a 12, 20, 24 and 28 run possibility, and these possibilities then very neatly covers the gaps between 8 runs, 16 runs and 32 runs encoded by the fractional factorials. These designs support linear models, and the drawback is that you get a really tricky confounding pattern, so they can be hard to upgrade if you want to unconfound confounded terms. If experiments are very expensive, we have another design family called the Rechtschaffner designs, which are saturated designs of resolution 5. And some literature studies of these designs have, looking into the statistical properties of these designs, have also concluded that these designs are also the optimal. We have also discussed L designs that are pure 3-level designs, or in one case a mixed 2-3-level design. You can estimate linear terms and selected quadratic terms with these designs, but there is no possibility that you can, they offer no possibility to estimate two-factor interactions. These designs, in the ones that are implemented in MODDE, has a fixed number of runs, which is a multiple of 9. And finally, we have the newest addition to the screening designs as a MODDE, the release of MODDE 12. We also have the definitive screening designs. They are available when there are at least 4 factors in an investigation, and they support models with linear and quadratic terms, but the quadratic terms are partially correlated, and if you're creating DOEs from the definitive screening designs involving many factors, the correlations among the quadratic terms grow rather rapidly, and at some point in time they are quite large. Here we have this table again that I was showing earlier on in the presentation, so you can go back and have an overview. The Plackett-Burman designs are the most compact designs. They require the fewest or smallest number of runs across all these families, but they also only support linear models. Another interesting and I think design family of growing awareness and spread is the definitive screening designs. They are very, very compact, and you can take the quadratic terms. But just remember that when you go up in the number of factors that you're studying, the correlations among the quadratic terms are growing rather rapidly. The designs being part of the fractional, the factorial design family and fractional factorial design family remain our first and second recommendations always if they are defined for a given situation, and that is because they are the most obvious one, or they are, for those it is most obvious how to proceed if you want to complement the design for instance, unconfounding purpose, or adding more terms to estimate quadratic terms in a screening DOE. So although they sometimes are on the high side as far as the number of experimental runs is concerned, the factorial designs and fractional factorial designs still remain our first recommendations in most situations. So with that, I thank you for your attention. I will shortly be back and try to respond to any questions if there are. So far, thank you very much for your time and attention.